Okay, let's start today's seminar. So today's seminar speaker is Rupert from Belgium. So he will talk about neutrino lines from dark matter decay induced by high-scale seesaw interaction. So please start.
Great. Thank you very much. And thank you for the invitation. It's really a pleasure to speak to all of you. I'm going to be talking about a recent project with Thomas Hamby, who I know spoke to you a couple of days ago, so you all know him well now. And it's on a model that we built where we tried to naturally explain very long-lived dark matter that can then decay in a way that is detectable, and in a way that has kind of a connection with neutrino masses. Um, so I'm going to kind of introduce and motivate this work. Then I'm going to move on to a toy model of stable dark matter, and then kind of the actual model where we have long-lived decaying dark matter connected to seesaw physics. So I'm not going to motivate dark matter because I think everyone here knows the story very well and understands uh, the story with dark matter and its motivation. Um, we know very little kind of for certain about dark matter, but one of the few things that we do know very well is that it must be either very long-lived or indeed exactly stable. Um, and this is already a challenge because most of the particles we know um, decay and indeed decay very, very quickly. So to come up with a model that where dark matter kind of naturally is stable or lives very long is already not that easy. So let me say something very quickly about stability. Um, so we know that indeed that there are four stable particles in the standard model, um, and they're all kind of stable for very fundamental reasons, and none of them are ad hoc. So you put in the gauge symmetries, you put in Lorentz symmetry, you put in the particle content, and then the particles that are stable are just stable like that. And the standard model is often kind of an inspiration for physics beyond the standard model. And so the fact that the standard model particles, which are stable for fundamental reasons, is kind of suggestive, at least, that possibly dark matter stability should have a deeper reason, that there shouldn't just be some kind of Z2 that people kind of put in. Excuse me. And so a couple of examples where that's been done in kind of well-known instances. One is, say, is minimal dark matter, where dark matter is a 5-plet. And the point is that there's no renormalizable interactions that can induce its decay. So kind of the dark matter stability proceeds very naturally. Another example of this which is kind of an inspiration for the model that I'll talk about a bit later, is hidden vector dark matter, where you have some gauge symmetry that's spontaneously broken, but there's a remnant kind of accidental symmetry that stabilizes the dark matter. And so these are kind of, I feel, at least more attractive dark matter models because the stability of the dark matter emerges kind of naturally, and is not just put in by hand to make something work. On the other hand, decaying dark matter is an interesting scenario. It's an interesting thing to consider because if you have dark matter that decays to standard model particles, you open up a new possibility of observing dark matter via detecting these decays. And the most kind of interesting types of decays are two-body decays to photons or to neutrinos, because these give you photon or neutrino lines, which basically cannot be replicated by astrophysical backgrounds. And so these are kind of considered smoking guns for dark matter. So these types of decays are particularly interesting to consider. But we're still left with the question of if dark matter does decay, why does it have such a long lifetime, especially compared to all the other particles that we know about? Of course, one solution to this is to introduce some extremely small couplings. This is certainly possible, but it doesn't really seem natural, and it's not very appealing from a model building perspective. Another kind of more appealing way, I think, is to have some suppression by some large scale. And the way this works is basically to have some dark matter model that looks stable and to add some UV physics that can destabilize it. So we can think about this a little bit and get some general principles from this. So kind of the first thing we can do is think about some dimension 5 operator, which emerges from UV physics. This is the lowest order effective operator. And then kind of all things being equal, the dark matter width schematically has the form of dark matter mass cubed divided by the new physics scale lambda squared. There's some couplings in there, which I'm not going to think about, and there's a 1 on 8 pi, which typically enters into a width. And then you can say, well, if the new physics scale is no larger than the Planck mass, and if this decay is into some kind of standard model particles, then the typical limit is about, on the dark matter lifetime, is about 10 to the 22 seconds. We'll see this more precisely a little bit later. But in this case, if we take this limit and this bound on lambda, then dark matter should be quite light. It should be less than about an MeV. And so if you have some dimension 5 suppression, you need either very light dark matter or you need some extra suppression, so some small couplings or some loops or something like that. Otherwise, this suppression isn't enough and the dark matter decays too quickly. So then we can go to next order in the new physics scale, and we can consider some kind of effective dimension 6 interaction. And then just again, by dimensional analysis, you have a width which scales as dark matter mass to the 5th divided by the scale to the 4th power. And then again, if the dark matter mass is, if the new physics scale lambda is no larger than the Planck scale, then you can get a slow enough decay, even if dark matter is as heavy as about a PeV. Keep in mind also, that this dark matter mass, it's dark matter mass to the 5th that I put here, but you can also replace it with some other kind of dimensionful numbers, some verbs or whatever, but just schematically, it's dark matter mass to the 5th. And so to get some idea of numbers, we could say that the dark matter mass or whatever dimensionful thing enters into the numerator, if that is roughly of the electroweak scale, and if the new physics scale is the 10 to 15 GeV, which is motivated by, say, seesaw physics or gut physics, then the lifetime is about 10 to the 27 seconds. And that's interesting because that's in reach of neutrino telescopes and other experiments. And so this dimension 6 suppression is enough to make dark matter sufficiently long-lived, but is kind of the right value that it's possibly detectable in the near kind of future. And if you can engineer this UV physics to be, say, the seesaw, then you can provide a connection between why neutrino masses are so small and why the dark matter lifetime is so long. And that's quite a nice connection to make. So one thing that kind of pops into mind when you think about UV physics destabilizing dark matter, and when you think about the seesaw in particular, is the well-known example of Myeron dark matter. So just a reminder, the Myeron is the pseudo Nambu-Goldstone boson that arises when you spontaneously break lepton number symmetry. And that's typically done at the seesaw scale. And so initially, this looks like a very good candidate for what I'm talking about, because you can compute the rate of Myeron to nu bar. This has been done many times, and you see that it scales as the Myeron mass times the VEV divided by lambda to the 4th, where lambda is the seesaw scale. It's the scale of lepton number breaking here. And so this is exactly this kind of 1 on lambda to the 4th suppression that it gets you what you want, basically, that gets you that really long-lived dark matter. But the reason why this doesn't work is that when you go to 1 loop level, you have the decay of Myerons to charged leptons. And even though that's loop suppressed, that only goes as v on lambda squared. So it's like this dimension 5 induced decay. And the loop suppression is small, but it's not nearly as small as this v on lambda suppression. So dark matter is naively way too short-lived. And so you need some additional suppression. You need to introduce basically some very small couplings so that the dark matter avoids observational bounds. And this is somewhat unnatural because you're introducing small couplings, and also you lose the connection between neutrino mass and dark matter lifetime that you otherwise could have had. So that's why the Myron isn't kind of automatically a good candidate for very long-lived dark matter, unless of course the Myron is very light, as I said before, kind of below MeV, which is plausible. But for heavier Myrons, then this doesn't work. So now I'm going to go on to a toy model of stable dark matter, which is kind of consistent with what I was talking about having some stable dark matter and then having UV physics destabilize it. And by the way, I should have said at the start, if anyone has any questions or any comments, please feel free to interrupt it at any time if you want. So let's consider an example of stable and also multi-component dark matter. And it's a simple model where we extend the standard model by a gauge U1 symmetry. We introduce a scalar phi and a vector-like fermion chi that are both charged under this new gauge symmetry, and they're both singlets under the standard model. The verb of the scalar spontaneously breaks the symmetry. And so in the Lagrangian, we have all the kind of normal terms we expect. We have the gauge kinetic term, we have the kinetic and mass term for the chi, and then for the phi, you have kinetic term and the phi potential, including this portal to the standard model, this quartic interaction with the Higgs. The one term that's missing here is kinetic mixing. So one could expect something like a B mu nu fx mu nu term, where B is the hypercharge gauge boson field strength tensor. So this is missing, and we set this to 0. This is kind of technically natural, and one can see that if you set it at 0, you don't then induce it at one loop level. So it's kind of radiatively stable to keep it at 0. And kind of the symmetry reason is I suppose that if you ignore the chi for a moment, then there's a Z2 symmetry that arises under which the A prime is odd. And so to introduce this kinetic mixing would break this Z2 symmetry. So there's kind of a symmetry explanation for why this term isn't there. I point out also that we assume that the lambda m is very small, so that the mixing between phi and the Higgs is negligible. You can make it larger, and at this level, it doesn't really change the story. Another thing to think about, of course, is whenever you introduce a new gauge symmetry, one should think about anomalies. And since the chi is vector-like, however, there's no anomalies involved, so you don't have to introduce any more field content than what we have introduced. So equation 2 is just the same as equation 1. We have the same Lagrangian. As I said, the chi breaks the Z2 symmetry. And in principle, you have decays of A prime to chi bar. So if this is kinematically allowed, so if the A prime is sufficiently heavy, then this happens. And then, so the A prime is unstable, but the chi is stable, and the chi is the dark matter candidate. If, on the other hand, the A prime is not heavy enough to decay to 2 chi's, then the A prime is also stable. There's no other possible decays of the A prime or the chi, and so they're both dark matter candidates. And I haven't talked at all about production mechanisms, and I won't. The point is not about how to generate the abundance. The only thing I'm concerned with basically throughout this talk is getting stability. And so in this case, you have an exactly stable gauge boson and an exactly stable fermion as dark matter. And so if we want to generate a long-lived dark matter, the way we want to do this is by destabilizing it by some heavy new physics. And this has already been kind of outlined that this is going to be the seesaw mechanism. And so there's a simple way to do this, which is to introduce a right-handed neutrino, NR. And so it has couplings both to the left-handed and right-handed chi. Recall it's vector-like with these Yukawa couplings y left and y right. But apart from this interaction, we also want to explain neutrino masses. We need at least 2 stereoneutrinos for that. And so we introduce the typical type 1 seesaw Lagrangian. We have this stereoneutrino mass term, this Majorana mass term, and then we have this Yukawa coupling with the standard model. And then quite famously, the light neutrino mass matrix is given here in equation 5. And for a neutrino mass of about 0.1 eV, which is consistent with experiments, and for Yukawas of order 1, as is well known, this Majorana mass should be about 10 to the 15 GeV. By the way, throughout this, I'm going to treat everything as though there's just one family, so one family of standard model leptons, and only a single stereoneutrino, just for simplicity. Of course, for something realistic, we have 3 generations of standard model fermions. As we know, we need at least 2 right-handed neutrinos, and so that all the calculations amount to promoting numbers to matrices. But I'm just going to ignore that. And so we have this neutral fermion mass mixing, and the point is that with this mixing, instead of just having A prime decaying to chi bar, which is kinematically forbidden, now you have mixing between the chi and the light standard model neutrino, or sorry, the light neutrino mass eigenstate, and so that facilitates A prime to nu bar decays, and equivalently the chi, which was stable, can decay to a neutrino and something else. And so you have this typical kind of mass mixing matrix given here in equation 7. These M's are the Dirac masses, which are described as the Yukawa times Zvev, basically, where we recall that YL and YR are the couplings of chi left and chi right to the stereoneutrino, and Y nu is the coupling of the standard model to the stereoneutrino. This is all fairly standard, but the thing I want to highlight is that you have a number of terms here which are proportional to M right minus M left. So you have, in fact, 6 terms here. And so when Y left is equal to Y right, so when M left is equal to M right, then you have lots of zeros here, which changes things a bit. And we'll see the consequences of that very soon. But it's kind of an interesting feature here in this mixing matrix. And of course, so after you do this diagonalization, the masses of the fermions are pretty much as you would expect. So the light neutrino mass is m squared on mn. Again, you have a very large mn to explain the light neutrinos. The chi masses are roughly m chi plus some small correction, and the stereoneutrino mass is roughly mn. This is all at order 1 on mn. And so now, having kind of established the groundwork, we can compute decays and see what happens to, and compute the lifetime of these decays and look at the consequences of that. So now, as I kind of outlined, both the chi and the A prime do decay, but they do so with 2 very different rates. So let's focus on the A prime first. And the key thing is that both at tree level and, as we'll see, at loop level, the A prime decay width is suppressed by 4 powers of mn. So you have exactly that kind of dimension 6 style effect that gives you a very long lifetime. And at tree level, you can see it in this diagram here. Crucially, at the level of the amplitude, you have 2 lots of chi mixing into a light neutrino. So you have 2 lots of a stereoneutrino propagator, and in that propagator, you have a 1 on mn power, basically. And that explains why you have 1 on mn squared in the amplitude, and so 1 on mn to the 4th in the width. And all of these factors are basically what you expect very simply from looking at this diagram or the couplings and so forth. The key thing, or the only unusual thing, is this y left squared minus y right squared here, which I mentioned just in the last slide with from the mass matrix. So this means that as y left goes to y right, this decay width vanishes at this order so it vanishes at order 1 on mn to the fourth, and so the decay width is much slower. And basically the reason is that you have not one chi but two chis. You have the chi left and the chi right running in this diagram, and it turns out that when y left is equal to y right, the contributions to the amplitude from these two diagrams with the chi left and the chi right cancel out. So the only thing kind of to enforce is that y left and y right are not equal. That's just a little feature. So that's the two-body decay. Everything behaves as normal up to that small thing about y left and y right. And then we can consider multi-body decays. And there's an interesting thing here, because the common story is that 3-body and 4-body decays are always suppressed relative to 2-body ones, because you have the phase space suppression factors of 16 pi squared, basically, for each extra body. And while that is generally true, there's the interesting thing here, because when you have a VEV, so you have a 2-body decay and you have these Higgs VEVs, that comes with a V, basically, in the amplitude. And so you have two Higgs VEVs, so you have V squared in the amplitude, so you have V to the fourth in the width. But when you replace it with a physical particle, you get, instead of V, you get the typical momentum of the process, which is the A prime mass. And so if A prime is a lot larger than V, then this ratio, MA prime over V, compensates for the phase space suppression. So we see that in the 2-body, you had V to the fourth MA prime. In the 3-body, you have V squared MA prime cubed. So you have an extra MA prime squared over V squared. And then in the 4-body width, you have MA prime to the fifth and no V's. So you have a relative effective MA prime to the fourth over V to the fourth. And so because you get about a 16 pi squared for each body, each extra body in the final state, you expect that the 3-body starts to dominate over the 2-body when MA prime is about 4 pi times V. And indeed, this is exactly what happens. So it dominates, the 3-body dominates for MA prime larger than about 2.9 TeV. 4 pi times V is about 3 TeV. And the 4-body dominates slightly lower masses than 4 pi times this. The 4-body dominates for MA prime larger than about 12 TeV. Now, there's a couple of things to note. Firstly, we're summing over all different kinds of 3-body and 4-body decays. So we have, for the 3-body, we have A prime to nu bar H, nu Z, and nu lepton W. For the 4-body, we have more combinations. Another thing to note is that, so I was talking about replacing the Higgs VEV with physical particles like the Higgs, the Z, the W. In principle, one could also do the same with the phi and replace that with a physical body. But the problem is that when you do that, the only enhancement, you get is MA prime over V phi. And that, in fact, is just nothing other than a gauge coupling, which can't be too big by definition. And so there's nothing to be gained by replacing the phi VEV with a physical particle, because this ratio is not larger than 1. So you're not concerned with those kind of 3 and 4-body decays. You're only concerned with 3 and 4-body decays where you replace the Higgs VEV with a particle. Okay. So this was all at tree level, and we saw that in the Myron case, the problem arose at loop level. But happily here, there's no problem at loop level, and that the decay width still scales as 1 on the stereo neutrino mass to the 4th power. There's a whole bunch of diagrams you can draw. You can have a Z or an A prime mediating. You can have a Higgs or an eta. The eta is kind of the boson inside is the boson inside of the phi when you break down the phi into its 2 parts, because it's a complex scalar. And then finally, you have a diagram which essentially corresponds to kinetic mixing induced at one loop, which you do have now in this model between the A prime and the Z, which then decays into, goes into nu bar. And so it turns out that the first diagram with the Z in the loop dominates. And for when A prime and chi are much heavier than the electroweak scale, which is the right limit to take, as we'll see in a moment, you can compute the width, and you do have 1 on mn to the fourth. You have an extra log squared there because you have a log from the diagram, but it's 1 on mn to the fourth, and that's really the key point. And basically the difference between this and the myron is that in the myron you have a scalar, so you need to have some kind of chirality flip, and then that kind of, the loop computation becomes different to when you have a vector and you have no chirality flip. And that makes all the difference in between getting 1 on m squared for the scalar decay compared to 1 on m fourth for the vector decay. That's kind of the key point, and that's kind of known in other contexts, from things like Z decay to BB bar. People, it's kind of an analogous calculation. But there's not only, there's several loop level decays. So as well as A prime to nu bar, you can see that there's others quite quickly. So say, replacing in this first diagram, if you replace the Z with a W, you admit charged leptons, and so you have A prime to L plus L minus, where L is some charged lepton. And basically, because of SU2 gauge invariance, the rate of A prime to L plus L minus is the same as the rate as A prime to nu bar, up to kind of insignificant things like phase space, which don't really matter for a sufficiently heavy A prime. Another thing you can do is change around the loop so that you have another fermion inside the loop and you emit two bosons. So you can have things like A prime to ZH and A prime to W plus W minus. And some of these things are discussed in this very nice paper by Patel, Profumo, and Shakya, which came out about a year ago, where they talk about similar things, and they get a similar prediction to us. And that's kind of, in a slightly different model, they get a similar prediction. And this is this very nice thing that the width of dark matter to nu bar is the same as dark matter to charged leptons. That's a kind of a clear prediction of this type of model. And as we'll see quite soon, it's phenomenologically quite relevant, because the probes on dark matter decays to charged leptons and dark matter decays to neutrinos are at a similar sensitivity. So this is not only a kind of a robust prediction, but also a kind of a testable one. So something I should add, which maybe I kind of skipped over, which maybe was unclear, is, of course, when you compute this, you sum up the contributions at the amplitude level, and then you square them to get the width. So when I write kind of width tree level here in equation 8, or when I write width loop in equation 11, that's kind of assuming that one part of the amplitude dominates over the other. Of course, you need to add them up together, and in the final results, we get it from adding them up together, but this is kind of looking at them part by part. So I thought I should mention that. Now, just as in the multi-body decays, you have some enhancement at large MA prime, because essentially it is enhanced by m chi to the fourth on v to the fourth. You have no vevs here, essentially, because it essentially comes from the loop diagram gets rid of those. So you have some enhancement, and when you go to large MA prime, then necessarily m chi is also large, because m chi has to be larger than MA prime over 2 to forbid A prime to chi bar decays. So these start to dominate over, so the loop level decay, the loop level part of the amplitude dominates over the tree level part of the amplitude for larger A prime. And so in particular, if you take the case where MA prime and M chi are the same, then the loop contribution becomes larger than the tree level contribution once A prime is more than about 1.6 TeV. And crucially, the contribution is always, so for whatever ratio MA prime over M chi, the loop contribution is always larger than the tree level 4-body decay. And the reason this is important is because right at the start, when I was talking about why decaying dark matter is interesting, um, there was the fact that a 2-body decay to neutrinos produces a neutrino line, which is a smoking gun kind of dark matter uh, signature. And in this, we see that whether A prime is small or whether A prime is heavy, whether it's light or whether it's heavy, that there's always a 2-body decay that dominates, and so you always expect to see a line, which is a nice kind of clear signature of this model, which one can search for. So talking of this, let's get into some phenomenology. And there's a lot going on in this plot. So let me take a moment to kind of explain it. So firstly, this is a plot with the limits on the dark matter lifetime when it decays to nu bar. And although I've called this A prime, this in fact is kind of totally model independent. All I'm assuming is that you have dark matter that decays into nu bar, and I'm also assuming that you have flavor universal decays, which is to say that you have equal widths of decays to electron, muon, and tau neutrinos. And also note that one might say, okay, well, say my dark matter decays only into tau neutrinos, then perhaps all these bounds from electron neutrinos and muon neutrinos don't apply. But that isn't true, of course, because neutrinos oscillate. And so if you start off with all tau neutrinos from the dark matter decay, by the time they come to Earth and reach our detectors, you have a significant fraction which are electron or muon neutrinos. So this plot gets adjusted by a factor of 2 or 3, but not really by anything substantial. So this is an assumption, but changing this assumption doesn't change the story very much. And I shouldn't take too much credit for this because it's basically a compilation of all kinds of bounds that other people have put, in particular nice work by Camilo Garcia-Cieli and Julian Heek, also who were in Brussels a few years ago, plus a few extra things that have been added on. And so there's 3 types of bounds here. For light masses, there's 4 types of bounds. Firstly, you have the cosmology ones. So this dotted black line is the age of the universe. Dark matter should live longer than the age of the universe. That's the first thing. Then secondly, you have cosmology. This is quite a conservative bound done by Vivian Poulin and a few others, Julien Lesgauge. And the point of this is basically that you change late time cosmology, and then that kind of impacts how you interpret CMB and so forth. So that's the first thing. Then at low dark matter masses, you have these Barroxino, Kamland, and Super K nu bar E bounds. And so what you have is you have an ingoing electron antineutrino, and you have an inverse beta decay. So you have nu E bar plus proton goes to neutrino plus positron. Sorry, it goes to neutron plus positron. And the point here is that the energy threshold for the antineutrino is 1.8 MeV. Now, when you have a 2-body decay, each particle has an energy that's half the dark matter mass. So if the antineutrino has 1.8 MeV energy, that corresponds to a dark matter mass of 3.6 MeV. So kind of the lowest dark matter mass you can probe with that kind of experiment is 3.6 MeV, and that's what Barroxino does. And at this stage, the bounds aren't really any better than from cosmology. Then at heavier masses, you go to again looking at atmospheric neutrinos, but looking more at muon neutrinos. And I think the reason for that is that there's quite a good kind of theoretical understanding of that the muon and anti-muon neutrino flux. And then at higher energies, kind of above about 100 GeV, you go to kind of high energy neutrino telescopes. In particular, the dark blue and the purple lines correspond to ice cube bounds. And this kind of mustard colored line is to do with Fermi measurements of the gamma ray spectrum, excuse me. And so this is, and yeah, let me just emphasize again that this is robust. This doesn't apply to any particular dark matter model, but should apply to any case where dark matter decays into neutrinos. But we do have a specific model in mind where dark matter decays into neutrinos. So now we can look at what bounds we can put on the seesaw scale from this, and it looks like this. So to fix things, we take all the couplings equal to 1, and we keep the chi and the A prime mass the same. And again, we take flavor universal decays. And again, that assumption is not terribly important. The first thing that we see is that the bounds become stronger as the dark matter mass increases, and it becomes increasingly strong here. There's kind of an inflection point. And the reason is that for lower dark matter masses, the tree level decay dominates. And in that case, the dark matter width is proportional to the dark matter mass, just the dark matter mass, to the power of 1. On the other hand, when you get to higher masses, we saw that the loop level part of the amplitude dominates, and then the dark matter mass the dark matter width is proportional to the dark matter mass to the power of 5, at least when n chi is equal to ma prime. And so you have a much steeper dependence of the bound on the dark matter mass itself. There's a few extra colors here. There's a few extra lines. The brown, the gray, and the dark purple lines are new, and they weren't present in the last plot. And these are here. These are bounds not on dark matter decaying to neutrinos, but in fact dark matter decaying to charged leptons by looking at gamma ray fluxes. And the point is that since we know indeed that the width of dark matter into neutrinos and the width of dark matter into charged leptons is the same, then we can get bounds from that process as well. And it's interesting to note that at the top, kind of when you go to kind of 10 TeV or more, you have a lot of lines that are very close together, and some of these lines come from dark matter decays to neutrinos, and some from dark matter decays to charged leptons. And so the experimental sensitivity of both of these things is very similar. And so it's a good way to test, it means that there's good chances of testing dark matter, which has roughly the same width or the same rate of decay to neutrinos as to charged leptons. And so this is a nice feature, not only because it's a robust prediction, but because it's very much a testable one, as you can see by the fact that these lines are so close together. The other, I guess, the final thing to note in this plot is that you're probing, or it looks like you're probing very heavy dark matter masses, sterile neutrino masses. So indeed, when you get to about 10 to the 5 GeV, you're probing something around the Planck scale, a lot higher than the typical seesaw scale. And that's true. But of course, the way to relax this, the way to get down to smaller sterile neutrino masses, smaller values of Mn, is simply to reduce the coupling. So if we go to the width, assuming that the loop process is dominant, you have 2, 4, 10 powers of couplings, be they the gauge coupling or the Yukawa couplings, and 4 powers of the mass. So if we go back to this plot, and if we assume that all these couplings are 0.1 instead of 1, then the bound on Mn is correspondingly 2 orders of magnitude weaker. And so this isn't to say that all models with 10 to the 5 GeV or heavier are ruled out because you're going above the Planck scale. It's just to say that you would want smaller couplings involved. So that's a lot of time spent on the A prime decay. Of course, the other guy that's decaying here with a different rate is the chi. And the A prime decay was so slow because you had A prime to 2 chis, and so you had 2 lots of chi to nu transitions, each of which came with a 1 on Mn factor. If you only have the chi by itself, it can decay in various ways, but this decay necessarily scales as 1 on Mn squared. So it's much faster than the A prime decay. And the width is given in equation 12 here, suggestively around about 1 second. And we see that the width goes as, the lifetime goes as Mn squared. This is from the decays to H nu, Z nu, and W lepton. the decays to eta, eta is again the kind of the scalar within inside the phi, or to a prime nu, if kinematically allowed. These are relatively suppressed. Basically, it comes back to that story again about v over v phi, and whichever vev you kind of omit in this diagram. And if you go to even lighter chi, then you have a smaller width because you have a free body decay to fermions. And so this width, or this lifetime, is suggestively put at around about 1 second, and that makes us immediately worry about BBN, because these decays produce charged and relativistic particles. So you could easily worry that if you want to make Mn, say, large enough that the dark matter decay, the A prime decay, avoids all constraints, then you could worry if the chi decay is quick enough to happen before BBN and stop it from messing everything up there. And the answer is that happily you can. And this is a plot to demonstrate that fact. So again, we set couplings to 1. We take the smallest allowed A prime lifetime, which is to say that for all other parameters, we keep the smallest allowed stereoneutrino mass, which can be attained just from this plot before this bound on Mn. And so setting BBN lifetime at 1 second for simplicity, we see that as you take large values of A prime, or as you take large values of M chi over MA prime, you can easily avoid this bound, and you can easily decay before BBN. I guess a way to see it, well, there's a couple of ways to see it. I guess the first thing is that you have this interesting ratio, somewhat interesting, somewhat kind of numerology, but the lifetime of BBN, 1 second, divided by the kind of rough lifetime of dark matter, which is about 10 to the 25 seconds to avoid these constraints, is roughly the ratio of the neutrino mass divided by kind of the natural seesaw scale, 10 to 15 GeV. Both of these ratios are 1 over 10 to the 25. So it means that if you have some 1 on Mn squared suppression of one decay relative to another, then that ratio roughly gives you the difference between dark matter that's just long enough lived to avoid constraints and something that's kind of just inside BBN. So to see it in equations, you can take the ratio of the chi mass over the A prime mass, and up to some phase space factors and up to some kind of order 1 factors, it looks like, and up to some pi's as well, it looks something like this. And so if you fix, you can see many ways to kind of easily make the chi lifetime much smaller than the A prime lifetime while keeping certain things fixed. So if you fix the neutrino mass, say, and if you make and if you fix the A prime lifetime to make it just out of reach of experiments, then things like making stereoneutrino mass larger, or by increasing the chi mass relative to the A prime mass, are things you can do to make this lifetime short. And so it's this interesting thing of having at the same time one very long-lived particle and one sufficiently short-lived particle. But in the end, it's quite possible to do that. Let me comment just briefly on what happens if we have a non-abelian model. There's not a lot to say, but one should keep it in mind, because we took the simplest possible scenario of just having a U1 gauge extension, but you could easily have say an SU2 extension, and there the chi and the phi are both charged. In this case, they're doublets is the simplest realization, and the dark matter is again gauge bosons, but this time it's a triplet. So and it's protected by custodial symmetry. And this by itself is the hidden vector dark matter model of Thomas, which I referenced in one of the early slides. And now if you introduce seesaw physics to explain neutrino masses and to destabilize this dark matter, you have very, very much the same story. Still dark matter is suppressed by 1 on Mn to the 4th. Basically, the only thing that changes is SU2 factors. But there's one nice feature here, which is that right at the right at the start of introducing this model, I said that we would assume that there's no kinetic mixing. That was an assumption, and we had some justification, but still, that's something that had to be put in by hand. And of course, the advantage of the abelian scenario is that there's automatically no kinetic mixing. You can't write down such a term once you have a dark SU2, for instance. And so that's just one extra thing that makes this a slightly nicer scenario, but otherwise it is exactly the same. So that's everything I want to say about this model, actually. But to summarize, because there's been a few things that I've said, I guess the starting point, the motivation is that decaying dark matter is a really nice scenario because you open up kind of a new way of discovering dark matter. But of course, you have this challenge of explaining such a long lifetime. And that kind of the most natural way to do it, perhaps, is to introduce some UV physics scale which destabilizes it. And in particular, some effective dimension 5 operator is generally not enough unless the dark matter is very light or unless you have some very small coupling. But if you can manage to have the dark matter decay from some effective dimension 6 interaction, then you can get to a lifetime that is not only long enough, but is kind of, I guess, at the same time, short enough to be probed by present experiments. We constructed a specific model where this dark matter was the gauge bosons of an abelian or equally a non-abelian symmetry, if you want. And there's some kind of nice connection between dark matter lifetime and neutrino masses, and there's some nice signatures. And I suppose the final thing I should do is to advertise that there's another paper coming soonish, next month, I hope. So if you found this interesting, or even if you didn't, you should look out for that on the archive soon. So thank you very much for your interest.
Thank you very much. So now is question and answer time. Any questions?
Let me ask a question.
Okay.
So you said that you don't mention about the origin of abundances. So what if the dark matter abundance? Do you have any rough estimate of your parameter space to explain the abundance?
To explain the abundance.
And which may be related to this your signal. And basically that will constrain your parameter space, right?
Conceivably, I mean, it depends. I think one could imagine different ways in which this abundance arises. So
okay, right. I mean, if you assume some kind of freeze out process.
Yeah, so that's very interesting, and it would be interesting to consider if you have some, what the connection is. I suppose that necessarily the connection with the standard model, the interaction with the standard model is quite small, because you want to have something that's long-lived, and if you have
okay, so basically
interaction with the standard model, then the decays will be too fast. So it's unlikely to be a WIMP scenario. One could consider conceivably freeze-in, but that's kind of, I think, difficult to manage. We had in mind kind of more like just some secluded production.
So you say freeze-in may not work in your scheme.
Yeah, well, I'm not sure.
Probably, yeah. What's the typical coupling size? Okay, can you go back to this A prime from one loop?
Sorry, which slide?
Yeah, from here. So basically, A prime couples to nu, and then okay, I cannot see immediately. But yeah, basically, if the coupling size order of 10 to minus 10, maybe it's right regime for freeze-in, right?
Yeah, the typical thing for freezing. I'm not sure.
Okay, good. Also, another question was, the lifetime, you assume that this is longer than the age of universe. But can it be shorter?
The dark matter, no. So this is the result basically by this is this black line. So by Poulin-Lesgauge, and I'm not going to pretend to understand the cosmology very well, but I think that the idea is basically that if you have some heavy dark matter that decays into something, and you assume that that thing is
Yeah,
very, very light.
that's
So
due
it's relatively
to neutrino production. It contributes to dark what is this? Dark radiation.
Yeah, exactly.
Okay,
So
okay.
they say that no more than some small
Okay,
percentage.
yeah, that's
can
right.
decay.
Okay, good.
Yeah.
Good. Yeah. Okay, good. Thanks.
Thank you.
I had a question. Would you remind me what are the typical mass scale for dark matter? Yeah, well, so your dark matter has a mixing with standard model neutrino.
Yes.
And
well, sorry, the dark matter is the A prime. It's not the chi.
Oh, sorry. I thought a chi particle. Well, would you go back to the previous slide?
Yes. Or maybe a few.
Maybe. Oh, yes.
In this initial model, so we had this multi-component, and so the dark matter was both the A prime and the chi. And then the point here was that the A prime decay goes as 1 on m into the fourth, which is slow.
Yeah, and then I'm talking about chi particle.
Yeah.
Is that so? I was thinking it's also a part of dark matter. Is that right?
So no. So the key difference between, sorry, maybe I should have explained this a bit more carefully. I guess the key point, but the key difference is that in the A prime decay, as you see in this, say, tree level diagram, you have two lots of you have each chi to neutrino mixing gives you kind of a 1 on mn. So the width for A prime to nu bar is 1 on mn to the fourth. Whereas if you have just a chi, the chi decays as 1 on mn to the squared. So it's a much faster decay. In fact, we were worried that it would interfere with BBN, but we found that the lifetime of the chi should be less than 1 second to avoid BBN and other issues. So in this case, the chi is not dark matter. It has to decay early on, and it's just the A prime.
I see.
Does that make sense?
Yeah, and you just put the mass of chi by hand.
Yeah,
right?
Exactly. So the chi mass, it comes from going back to this initial model. It's just this parameter here, m chi, and similarly the dark matter mass A prime is simply just from the vev of the phi. So the dark matter mass here is gx times v phi. So these are both things that you basically put in by hand. The vev of the phi can be whatever it is, m chi can be whatever it is, and then the thing that we want to enforce is that ma prime is less than 2m chi, so that you don't have the immediate A prime to chi bar decay.
I see. Okay. All right. Yep. Thank you.
Thank you.
So hello. Thank you very much for nice talk. I have a question about this kinetic mixing in the non-abelian case. And isn't there dimension 6 operators that they generate effective kinetic mixing? For example, B mu nu times trace of phi dagger W mu nu phi.
Conceivably, but at the renormalizable level, there isn't.
No, yeah, no, not in the renormalizable level, but
Yeah.
in the higher dimension operator, dimension 6 operator, that I think that we can write b mu times trace of phi dagger. Phi is a SU to doublet.
Yeah.
Presumably that gives W hidden W mass,
Mhm.
right? And
Yeah. Okay.
phi dagger W mu phi. Just
Yeah.
oh, we don't have to take a trace. Actually.
Yeah. Yeah.
Yeah,
Okay.
sorry. Yeah, phi dagger W mu phi and B mu. This dimension 6 operator. So of course the new physics scale lambda is very high. Then it may be the kinetic mixing will be very small. But anyway,
Yeah. Yeah. I
matter
mean
of principle, I think. Yeah.
that's certainly true. I guess it's a matter of having new physics that doesn't induce that particular operator.
Yeah.
So in particular, if we take the type 1 seesaw, then I don't know, but I would guess that you don't generate that. I'm not sure. Or if you do that it's small enough. I guess, which is to say that just because you can write down an operator, I guess it depends on whether the UV physics generates it or not.
Yes.
But that's certainly a good point.
And could you show the last slide, conclusion slide? So
Mhm.
here you say in the second line from the bottom,
Mhm.
you say there is a direct connection between dark matter lifetime and the Neutrino masses.
Mhm.
So how robust, I mean, this statement? Under what assumptions? Could you remind me again? Under what assumptions this can be?
So it's not. I mean, it's not very robust, and I'm not going to pretend that it's kind of it's a one-to-one. But I guess it's the fact that you have the same parameters, namely the kind of the Yukawas and the stellar neutrino mass, the same parameters that enter into the light neutrino mass matrix also enter into the dark matter lifetime. So I mean, we look at the width, and basically, I mean, you have things like the 1 u to the 4th, the mn to the 4th.
Okay, yeah.
There's obviously other factors, and so I can't measure the lifetime of the dark
Mhm.
matter and say therefore the neutrino mass is this.
Mhm.
But if I the point is, I guess, if I choose some values of couplings, then I can make a measurement and I can say what the seesaw scale is. And this is, I guess, in contrast with, say, the Myron case, where you lose the connection because you have to introduce some extra small parameter into the dark matter lifetime, whereas you don't here. So ultimately, it's not a very robust statement, indeed, but it's about saying, okay, you can see some connection.
Okay, thank you.
Thank you.
Okay, any other questions or comment? Okay, if not, let's thank to Rupert again. Thank you very much for the nice talk.
Thank you.
Thank you very much.
Thank you.
Bye-bye.
You.
Okay. Rupert, please send me your slide.
Sure.
Yeah.
Yeah, will do. And thank you again very much for the invitation.
Oh, thank you very much for the nice talk we It's very good.
Thank you.